So the gradient is important not only in calculating directional derivatives, it plays many other roles in multivariable calculus. So our goal is to develop some intuitions about the meaning of the gradient. So we have seen that the directional derivative of the function at the point, let's say a comma b, in the direction of the unit vector u is written as the dot product between the gradient and the unit vector u. So let theta be the angle between the unit vector u and the gradient vector of the function f of xy. Then the directional derivative of f along u can be written as the dot product as follows. D sub u of f of x comma y is equal to the gradient of f of x comma y dot with the unit vector u. Now we learned in the dot product lecture that using the geometric interpretations of the dot product, this can be written as the magnitude of the gradient vector multiplied with the magnitude of the unit vector times cosine of theta, for theta is the angle between the unit vector and the gradient vector. But u is the unit vector, therefore the magnitude is equal to 1. Thus we got that the directional derivative can be written as the magnitude of the gradient multiplied with cosine of theta, again for theta is the angle between the unit vector and the gradient vector. We know that cosine of theta is bounded between -1 and 1 because of the amplitude of cosine is equal to 1. So therefore the directional derivative has its maximum value when cosine of theta is equal to 1. A quick note here is that cosine of theta is bounded between -1 and 1. It follows that the directional derivative has its maximum value when cosine of theta equal to 1, which corresponds to theta equal to 0. Therefore, the directional derivative has its maximum value, max value, and f had its greatest rate of increase when the gradient vector and u point in the same directions. And the actual rate of increase is that the directional derivative equal to the magnitude of the gradient vector. So from here you can get that the directional derivative of the functions is equal to the magnitude of the gradient of the function, and this is the actual rate of increase. Now similarly, when theta is equal to pi, we have cosine of theta equal to -1. F has its greatest rate of decrease when the gradient vector and the unit vector u point in the opposite directions. So f has its greatest rate of decrease when the gradient of the functions and u point in the opposite directions. And the actual rate of decrease is you have the directional derivative equal to negative of the magnitude of the gradient. And then for the last case, when theta equal to pi over 2, that is the gradient vector and the unit vector form a 90-degree angle. When that is the case, cosine of theta is equal to 0, then the directional derivative is equal to 0. So notice that in this case, the directional derivative is equal to 0. And again, remember the directional derivative calculate the rate of change of function at the point of consideration. So in the case where the unit vector and the gradient vector form a 90-degree angle or they are orthogonal to one another, there is no rate of change, or the rate of change is equal to 0. So we can make the connection between our observations in these three situations with an example shown in this figure. So in this scenario, a biker rides along a path. So the temperature T changes at a rate that depends on the cosine of the angle theta between delta T and the directions of motions. So in this particular direction, the temperature changes at the rate of the magnitude of delta T times cosine of theta. And you have in this particular direction, the maximum temperature increases in the gradient directions. This is where the gradient vector and the unit vector point in the same directions. Now, the temperature rate of change is 0 in these directions because the directions of motion is orthogonal to the gradient of the temperature. So that is just one scenario that you may see in real life. So from our observations in the case of theta equal to 0 and theta equal to pi, we can actually summarize these observations as follows. That is, the gradient vector point in the direction of the steepest ascent at the point x, y, while negative gradient vector at x, y point in the directions of the steepest descent. So I'm going to draw that conclusions here. There are two scenarios. That's when theta is equal to 0. The gradient vector points in the directions of steepest ascent. And when theta is equal to pi, negative gradient of f points in the directions of steepest descent. That is one property of the gradient. Another property of the gradient that you've already seen in the last example is that the gradient will be perpendicular to the tangent line of the level curve at the point of considerations. And we're going to quickly show that is the case in the following derivations. So we're going to consider this figure. You can see the curve in greens are the level curves of a surface, and this level curve can be described using f of x, y equal to some constant c. For f of x, y is a differentiable function, where x is a function of t and y is also a function of the parameter t. Therefore, the equation of the level curves can be written as f of x of t, y of t equal to c. Now what we're going to do is we're going to show that the gradient vector is going to be perpendicular or orthogonal to the tangent vector of the level curve at the point of considerations. To show that, we're going to take the derivative on both sides of this equation with respect to t. So we're going to do d dt. And on the right hand side, you have d dt of c. And the derivative of a constant with respect to t is equal to 0. And on the left hand side, you're going to use chain rule for function of one independent variable. Now the independent variable that I mentioned here is the parameter t. So therefore, you have the chain rule as follow. Partial f partial x times dx dt plus partial f partial y times dy dt. And that is equal to 0. Now, as you can see on the left-hand side, this is actually going to be a dot product between two vectors. That is the vector of the form partial f partial x, partial f partial y, dot with the vector dx dt, dy dt, and is equal to 0. So we learned earlier this vector is actually the gradient of the function f. So this is the gradient of f, dot with this vector dx dt, dy dt. So dx dt, dy dt is actually the component of the derivative of the vector value functions of the form r of t equal to x of t I plus y of t j. So therefore, when you take the derivative of this vector value functions, you have x prime of t I plus y prime of t j. And r prime in this case is the tangent vector of the vector value function whose components are x of t and y of t. In this case, you have x prime of t means dx dt and y prime of t in this case dy dt. So technically what you have here is that this is the gradient vector dotted with r prime of t, and that is equal to 0. This shows that the gradient vector of f is normal to the tangent vector or orthogonal to the tangent vector. So therefore, it's going to be normal to the curve or orthogonal to the level curve. So this implies that the gradient vector is orthogonal, or normal for that matter, to the tangent vector r prime of t. So we just showed that another property of the gradient is that the gradient is going to be orthogonal to the tangent vector of the level curve at the point of considerations, as you can see in this picture, as well as in this picture. So we're going to see some example that relate the properties that we just discussed into some actual functions. So in example 4, let f of xy equal to x to the 4 times y to the negative 2 and the point p equal to 2, 1. Would like to find the unit vector that points in the direction of the maximum rate of increase at p. So when you want to find a unit vector that points in the direction of maximum rate of increase at p, from our discussions we have that the gradient vector and the unit vector point in the same directions where theta is equal to 0 or cosine of theta is equal to 1. So to find the unit vector u, that is, you just need to find the gradient vector in this case and then normalize it. That means you find the unit vector of the gradient vector. So let me show you how that works. So first, you're going to find the gradient vector. So you need the two components, f sub x. This is going to give you 4 times x cubed times y to the negative 2. And f sub y, which is negative 2 times x to the 4 times y to the negative 3. So the gradient vector is equal to 4x cubed times y to the negative 2, comma negative 2 times x to the 4th times y to the negative 3. And then you're going to evaluate the gradient vector at the point 2, comma 1. So you have x equal to 2 and y equal to 1. So 4 times 2 cubed times 1 to the negative 2, comma negative 2 times 2 to the 4 times 1 to the negative 3. And if we do the calculations correctly, we should get 32, comma negative 32. So that is the gradient vector. When we talk about directions of maximum range of increase, the gradient vector and the unit vector, you have to point in the same direction. So in this case, you just need to normalize or find the unit vector of the gradient vector. So the unit vector u in these directions is, so you have u equal to the gradient vector divided by the magnitude of the gradient vector. And the gradient vector is of the form 32, comma negative 32 divided by the magnitude of the gradient vector. You're going to have 32 squared plus negative 32 squared, or 32, comma negative 32 divided by 32 times square root of 2. And if you simplify this, you're going to get 1 over root 2, comma negative 1 over root 2. So that's how you find the unit vector points in the directions of maximum range of increase. Now I'm going to move on to the last example here. Now in the last example, I would like to consider the functions f of x comma y equal to negative x plus 2xy minus y. And the first question asks you to find the gradient of the function at the point 2 comma 1. So this should be easy for us at this point. So f sub x is equal to negative 1 plus 2y, and f sub y is equal to 2x minus 1. We're going to evaluate this partial derivative at the point 1 comma 2. You get negative 1 plus 2 times 2, or this is equal to 3, and f sub y of 1 comma 2 is equal to 2 times 1 minus 1 is equal to 1. So the gradient vector of 1 comma 2 is equal to 3 comma 1. Then the next question, you want to find the directional derivative of the functions at the point 1 comma 2 along the directions of u equal to negative 1 over root 2 comma 1 over root 2. And again, you have seen this kind of problem earlier in the lecture. When you see something like this, you need to double check to see if the given vector is a unit vector or not. If it is, you can proceed with the calculation of directional derivative. If not, you need to find the unit vector of the given vector. So in this case, if you do the calculations, you will see that u is indeed a unit vector. So here I'm going to proceed with the calculations of directional derivative of the function at the point 1 comma 2. So you have, this is the gradient of f of 1 comma 2 dot with u. So you have 3 comma 1 dot with negative 1 over root 2 comma 1 over root 2. And you're going to have negative 3 over root 2 plus 1 over root 2. Or this gives you negative 2 over root 2. You can actually simplify this a little bit further. That is, if you radicalize this fractions by multiply top and bottom by root 2, you're going to have negative 2 times root 2 over 2, or the result is equal to negative root 2 only. So the next question asks you, what does the sign of directional derivative tell you about f? So since the directional derivative of the function at the point 1 comma 2 in the direction of the unit vector u is equal to negative square root of 2, which is a negative number, that is, the function is decreasing in the directions of u. So if you stand at the point 1 comma 2 and you want to walk or you want to climb in the directions of u, that is, you're going to go down in the directions of u. So since the directional derivative of the function at the point 1 comma 2 equal to negative root 2 less than 0, the function is decreasing in the direction of u. In the next questions, they ask you in which direction is the directional derivative of the function at point 1, 2 the greatest? And then what is the slope of the graph in these directions? So this is another way to ask you what is the direction of the steepest ascent, or what is the greatest rate of increase, or what is the direction on which f has its greatest rate of increase, and what is that rate? From our discussions earlier, the function has its greatest rate of increase or the maximum rate of increase when the gradient vector point in the same direction as the unit vector u. So the unit vector u I just mentioned has nothing to do with the unit vector u right here. Okay, so now in that case, what you do is you need to find the gradient vector at point 1, 2, which we did in part A, and to find the directions in which you have the directional derivative is the greatest. That is, you just normalize the gradient vector. So here, u is equal to the gradient vector divided by the magnitude of the gradient vector. For the gradient vector is equal to 3, 1, divided by the magnitude of the gradient vector, which is 3 square, plus 1 square, or 3, 1 divided by square root of 10. Well, you have this vector to be 3 over square root of 10, 1 over root 10. So that in these directions, directional derivative is the greatest, or in these directions, the gradient vector point in the direction of the steepest ascent, or in this direction, f has its greatest rate of increase. Now, what is the slope of the graph in this direction? So the slope of the graph is the gradient vector of the functions 2, 1, right, along the vector u. So this is the vector u. And this should be equal to the magnitude of the gradient, and the magnitude of the gradient is equal to square root of 10. And that's how you got it, the slope of the graph in these directions. Or another way to say that the actual rate of increase is equal to square root of 10. Now we're going to move on to the last questions. So in which direction is the directional derivative the least? This is another way to ask you, okay, what is the directions in which f has its greatest rate of decrease, or what is the direction of the steepest descent? That's another way to ask the questions. And then what is the slope of the graph in this direction? So we're going to calculate the directional derivative to be equal to negative of the gradient vector of f. So we're going to show that in a minute. Again, from the discussions of the properties of gradient vector, we know that when theta is equal to pi, or cosine of theta is equal to -1, that is the gradient vector and the unit vector u point in the opposite directions. So you have the gradient vector already, and you want to find the direction where the directional derivative is the least. That is u equal to negative of gradient of f divided by the magnitude of gradient of f. So you have these calculations already in part D. You just need to put the negative in front, and you get negative of the vector 3 over root 10, 1 over root 10, or you can write this as negative 3 over root 10, negative 1 over root 10. So in this direction, the directional derivative is going to be at 10 a minimum value, or going to be the least. Okay. Or another way to say that, when the unit vector and the gradient vector point in the opposite direction, f has its greatest rate of decrease. And when the directional derivative equal to negative of the magnitude of the gradient, in this case negative square root of 10, that is actually the rate of decrease, right? So the rate is still positive square root of 10, the negative to tell you that this is the rate of decrease. And this is also the slope of the graph in this direction. So the slope will show that the graph is going to go down. So that's it for me for directional derivative and gradient vector. So please let me know if you have any questions. Thank you.